Types of numbers. Welcome to the first video of covering the syllabus. So, types of numbers. What are numbers themselves? Just 1, 2, 3, We'll be learning the types of numbers. Okay, let's get into it. So, these three are the things that from the syllabus we are covering. One is the humble integer. What are integers? Integers are negative and positive natural numbers, including 0. They don't have any decimal component and only whole number. Example: negative 92, negative 11, 0, 5, 13, 4, 12, blah blah blah. Natural numbers. What are natural numbers? Okay, you will be asked natural numbers as well. Okay, I just didn't include them. Natural numbers are what you see naturally. Example: you can see a pair of twins. You can see 7 petals in a flower. You can see example 6.02 times 10 to the 23 atoms in a mole, blah blah blah. But you can never see 0 of a quantity or negative of a quantity, because that's just abstracting. 0 is just a placeholder. Negative numbers is something abstract, something to have an excuse of minusing, like below 0. So natural numbers are just 1, 2, 3, so on, so on. Basically positive integers. Okay, and integers themselves have 0 in them, and also negative natural numbers. Integers can be even or odd. Okay, even numbers are such n in 0, 2, 4, 6 or 8, like 12, negative 24, 38, negative 398, and etc. so on. Odd numbers are such n in 1, 3, 5, 7 or 9. Example: 15, negative 13, 35, negative 199. This is you may notice, but come on, sometimes you do not notice. If you right. Next, we have factors and multiples. The factor of a number are the numbers which divide the number evenly. Example: the factors of 6 are 1, 2 and 3. Factors of negative 36 are plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18 and plus minus 36. Now the negative thingy, you guys, I don't know if the negative factors are covered in any notes. I am teaching you negative factors because negative factors they will be used later on. For now, you need to know what they are. Okay, what negative factors are. Normally, you would just list down the positive factors because you'll be asked of positive numbers. But later on in the exam, later on in the syllabus, when we are doing quadratic factorization of quadratics, I will revise negative factors. Okay, for now you just need to know what positive factors are. Like 6 has 1, 2, 3. 8 has 1, 2, 4, 8. Or example, let's take a good number. What can you take? 100. 100 has the factors 1, 2, 5, 10, 25, 20, 25. Okay, off the top of my head, 50 and 100. Nice. Yes, these are the factors of 100. So on. Factors meaning and which divide the number evenly. The numbers that I wrote down, they divide this number, the 100 number, evenly. The factors of a negative number are the negative and positive of the factors of the whole number. See, this is what I mean about negative factors. Okay, now the multiples of a number is the times table of a number. Example: multiples of 6 are 12, 18, 24, 30, 36. The definition in my actual notes file what they have is that the numbers, meaning a multiple that comes in the times table of another number. Okay, example. You'll be asked, name a multiple of 6 in the list below. It'll be given like a list, example like this. It'll be asked to do multiple of 6. Example, okay, example. Then you choose 18. Example, multiple of 4, you choose 6. A prime. Let's go on to primes. You know what primes are. A prime number is a whole number that has only 2 factors. Remember, only 2 factors. One and itself. Examples: 2, 3, 19, 101. You can name other examples. Like, oh no. Yeah, but the primes you should know. The primes you should know. At least 2, 3, 5, 7, 11, 13, 17, 19. Example: 21, 23. Between, okay, 23 is enough also. You guys can look at primes. How to detect primes? Okay, remember, you want to carry out multiple tests when the question asks figure out a prime. If you cannot see a prime, or you are like unsure, like is this a prime or not, this test is for like non-calculator people. Example: 91. It may look like it is a prime, but no, it comes in table of 13. Yeah, that's weird. So you can do tests up to like 13 or 17 if it's that bad. But you need to know that 1, it should not be a multiple of 2. You guys can write it down. 1 multiple of 2, and the second is not a multiple. Okay, or this can be just even, not even, multiple of a prime. I mean, of course, a prime has only 2 factors. If it has another factor, it's a composite number, right? So yeah, these are the two things you need to look out for when looking out for primes. Okay, I have like so many questions about these. Okay, there's like only like one question in every paper about testing for primes, testing types of numbers, but it is very crucial to know how these questions do, because if God forbid, if you lose marks because of something very simple, then that's on you, I guess. Composite number is a whole number that has more than 2 factors. Example: 4, 10, 27, 100, 1000, blah blah blah. You guys know what a composite now is. Okay, it is not a prime. Okay, if it's not a prime, then it's a composite. If it's not a composite, it's a prime. Oh, and remember, 0 and 1 is not a prime number. Not a prime number. Why? 1 has only 1 factor. Primes have only 2 factors. For 0, I will leave this as an exercise for the one watching. Highest common factor and lowest common multiple. What are they? HCF between 2 or more numbers is the largest number which divides the number evenly. It keeps the factors shared by all numbers. You know what a factor is? The factors of a number are the numbers which divide the number evenly. So what is the HCF of the inputs? The HCF of the like between 2 or more numbers. Okay, it finds the number which divides all 3 with no remainders. LCM, lowest common multiple between 2 or more numbers, is the smallest common multiple that the numbers share. It collects every factor needed to rebuild all the numbers. Multiples meaning in a times table. It takes the inputs. Example, you have 3 inputs, and it checks in the times table that when does does this LCM thingy occur in all these 3. Okay, in the times table of the inputs that you give it in the LCM, and that answer that you get after doing LCM, that is the lowest common multiple. Because remember, multiples, you can multiply by another number to get another multiple of the inputs of the LCM. That's why it collects the lowest common multiple. Common that the inputs share. Multiple in the times table. Lowest, the first possible multiple that all 3 share. That's how the naming goes. To find LCF or LCM of 2 or more numbers, we do what's called prime factorization. Example, you have this. I'm doing it with 3 inputs. It's a little rare to get 3 inputs in your exam. You will only have 2 inputs in the exam. Okay, I'm just saying 3 inputs because it's like a little rare, so that's why I'm doing it with 3 inputs. When you do prime factorization, how do you do it? You gather all the numbers, then you write down the number you will divide it by. Here will be the smallest prime that can divide all 3. Okay, remember, this should be, what should you do this? Lowest prime. The lowest prime that comes to mind that can divide all 3. So example, it will be 2, then 3, then 5, then 7, then 11, blah blah blah. Normally you won't even reach 11 or 13. Okay, it's for like very the questions which are very terrible, which will annoy you. You know, I also had like the same thing during my exam, I think, when prime factorizing for a quadratic. Yeah. So here you will get like a very bad, a very small prime. It can divide all 3. Here 2 can divide all 3 fine. Here I chose 3 because 2 does not work. Why? These 2 are not even. Okay, it needs to be even to be able to be divisible by 2. Divisibility rules, I will do it at the end of the video, don't worry. So 3 divides all 3, this becomes 5, this becomes 2, this becomes 9. Need 3. Now, when you can't divide the numbers evenly by a single prime, example, we cannot divide all these by, example, 5 because 2 and 3 are not in the table, 2, 5 and 3 are not in the table, and 3, 5 and 2 are not in the table. That is the HCF. Now multiply the left column top to bottom, so you go downwards. The HCF is 6 in this example. There are like many examples you can see in like say my exams, Shingdi books, these new mathematics books, or the Cambridge and books that they have themselves. If we continue, we get the LCM. Divide the terms by which you can by the prime. Example, here this part was the HCF. This remaining here is the LCM. Okay, here we see we choose 2 because in these we can at least divide this by 2. So you go with this 3. The 3 is the lowest prime we can divide by. So we go here, and 5 we divide by 5, we get 1 1 1. Why 1? 1 is not a prime. Like I said, 1 is not a prime. You cannot just divide 1, and say no, it should be a number other than 1. Okay, you can't be that stupid. We get the LCM by multiplying the left column top to bottom. So if we multiply the numbers, we get the LCM. Now, a number written in its form, like example, this form 2, 3, 5, 7 with the powers as a product of primes with powers, it is in its index form. To get the index form of a number, we prime factorize it and collect the primes with their respective index. Example, 3 in its index form is 2 squared times 3 squared. 3 cubed is equals to 36. This is wrong. This is a mistake. Sorry. This is 3 squared. Okay. Very apologies. Okay. Example. How do we get this number? We do LCM of 36. 2, 2, 3, 3. 2, 18, 9. We cannot divide by 2, so we choose 3, and 3 works out fine. We get 1. Now, we write these out in multiplication. Now, we group them. We connect the prime factors. Okay, example, we have 2 2's, so you go 2 to the 2. You have 2 3's, you have 3 to the 2. Let's choose another number. Example, let's choose 64. You can divide by 2, then you go 16 to 8 to 4 to 2 to 1. I'm lazy drawing the lines. Okay, in examination you obviously have to prepare the ladder, then do this. Some people do it like this. Look. This. Like, what is this? I'm not saying that no method is wrong. It's not wrong. It's just that it takes a bit more area, a bit more space, of your working. So I'm just saying that use ladder method if you want to save a bit time. Yes, you shouldn't rush in the examinations, but I think that's a different kind of forms, rushing and like how fast you should do a paper and stuff. Here we see we have how many 2's? 2, 2, 2, 2, 2, 2. So you get 2 to the 6. This is 64 as our prime factorized form. So if it asks write the prime factorization of 64, you write 2 to the 6. That's it. Boom. It will accept your prime factorization form. Okay, because it is asking for prime factorized form. If it asks you prime factorize 18, so you will write 2 times 3 to the 2, because it is the prime factorization of 18. You get 18, 2, 3, 3, 9, 3, 1. So we have 1, 2 and 2 3's. 2 to the 1, we can ignore the 1. Okay, we do not need to write the 1 power, If we can find the HCF by taking the LCM, by taking the lowest power of each prime. If one prime is in common, in all numbers, ignore it. Example, 5 is in common, hence we ignore it. Next, we can find the LCM by taking the largest power of each prime. You can see that we include everything. Okay, if the numbers do not share one of the factors, you still take the factor, because you can think of it as like 5 to 0, and 0 is less than 1, so you take the highest power. And here we can see this. In the HCF, we take the lowest powers, as you can see. Here 1 is the lowest power. Okay, and like among all of these, okay, you can just pick any one. Okay, example, it may be like 2 to the 5, you choose 2 to the 2, blah blah blah. It's like, I cannot cover every example, obviously. Here we choose 3 to the 1 because among these powers, 3 to the 1 is the highest. I hope this is clear. Okay, if you want, comment down below if you want a video explaining these in depth. Next, squares and cubes. When some number is multiplied by itself, aka when a number is squared, it gives a square number. Example, 4 times 4, 4 being multiplied by itself is equals to 4 squared is equals to 16. A perfect square is by squaring a whole number. Remember, a whole number. Okay, it cannot be a fraction, it cannot be a decimal, only a whole number. Meaning a integer. Okay. When squaring a number, the index of primes in index form of a number is multiplied by 2. Example, in 18 squared, we know the prime factorization. 2 times 3 to the 2. If we multiply the power, we can distribute this like so, and we can see the prime factors of 18 squared are the following. You can also see this by doing it in this fraction. 18 squared is equal to 324, and if we do prime factorization of 324, 2, so this is 1, 6, 32, 16, 2, 81. Now 81 is not divisible by 2, so 3, we get 27, 3, 9, 3, 3, 3, 1. So you get 2 squared times 3 to the 4th power, and you can see, okay, that we derive this. If we square this, then we observe that the powers are multiplied. Okay, you can do this for any number you want. Okay, this is the observation we see. Later on, when you do indices, you will understand this a lot better. Okay, why this works. So for now, keep this at the back of your mind. When some number is multiplied by itself 3 times, okay, when a number is cubed, it gives a cube number. Example, 4 times 4 times 4, 4 being multiplied by itself 3 times, is equals to 4 cubed is equals to 64. A perfect cube is by cubing a whole number. In cubing a number, the index of the primes in the index form of a number is multiplied by 3. Example, 18 cubed, we multiply by 3 and you get this big number. Example, 6 cubed gives us 2 times 3 cubed is equals to 2 cubed times 3 cubed, because the 1 is invisible. We do not write the 1s usually. So if we just do this, we basically do 1 times 3, which is just 3 itself. And this gives us 216. And we can also see it for ourselves. If we can do this, 108, 54, and this will give us 27. 1. Now, I did not mention this, but this is to reverse. Okay, yeah, no, I did mention it. Okay, let's continue. Then I will tell you what I want to say. The square root of this thingy, this is called the radical, by the way, gives the quote root of the original positive number which was squared. Example, 16 squared gives us 4 because 4 was originally squared. This is a misconception many people have. A square root does not give us plus minus. When solving, we take plus minus. Okay, this is a very big difference. Okay, you will get to this in the algebra chapter. For now, you have to know when we do square root, it only gives the positive root. Only. Remember, only the positive root. Okay, because if we just go putting plus or minus, Yes, you may be at the mercy of the marking scheme having this like a plus minus in the brackets, but it sometimes won't be, so you got to be careful what you are doing. Okay, because computing example, you want to compute 5 plus root 9 over 3. This will give us 8 over 3, because we take this to be positive 3 normally. Okay, when you're normally doing it, so you have to keep this in mind. It gives the positive root, and taking the square root of the number, index of primes in the index form of a number is divided by 2. Example, you have 225. If we prime factorize it, we get 3 squared times 5 squared. We cut the square root with the square, and we get this thingy that I'm doing here. This is cutting like the reverse operations. You know how multiplication and division cancel out each other? And this is the same thing. Okay, addition and subtraction cancel out each other. This is the same thing. Multiplication and squaring. Taking a square root and squaring cancel out each other. Okay. You guys can also see square root of 3 times 5 whole squared. We cancel out and you get 3 times 5 also. Commutative. Okay, we will see these this thingy later on when we do the like the board mass and also indices. A cube root, which is by this, okay, a radical index tree. Okay, this is called the index. Okay, the index, or like in my previous videos, the metric video, the radicand. Who on earth calls it a radicand? Okay, let's call it a cube root. Okay, please, for God's sake, let's call it a cube root. Or the cube root gives. Okay, I didn't write this. It's a typo. Sorry. Gives the root of the original number which was cubed. Example, 3 cubed of 64 gives us the regular number 4. Why did I not write negative about positives? Cube root of a negative number gives us a negative number. You cannot take the square root of a negative number because that is invalid. A calculator will say no. Okay, it gives us something, but it's out of the scope of the syllabus. If you want to see what it gives us, be my guest. When taking the cube root of a number, the index of primes in index form of a number is divided by 3. Example, this number in its prime factorization form, we can get the powers out of there. Okay, or just simply 3 to the 3 over 3 times 5 to the 3 over 3 is equal to 3 times 5. The powers divide. Same here. You can think of this as 3 to the squared over 2 times 5 to the squared over 2. These are cancelled out to 1, so this is 3 times 5. To compute the square roots and cube roots, first factorize the number into its index form and doing the upper mentioned processes. Upper mentioned meaning these processes. Okay. To know if a number in index form is a square number, see if the powers are a multiple of 2. To know if a number in index form is a cube number, several powers are a multiple of 3. If not, you may multiply or divide by some constant, example k or r. Then you use indices to find the appropriate constant. Now, questions in paper 2 will, and in paper 1 sometimes, will say like, hey, n is a prime factorization, n over r is something like a cube, find r, or n, like example nm is a square, find m. Okay, anything. For now you can skip these if you are able to do this by yourself, and well and good. Else I will else the next video will be about solving this specific question. Okay, or if you guys want, okay, no, let's do this. We will revise this when we do indices. That way we can fully understand these types of questions. Yeah, good trade-off, right? Good. So if you are in the future and the indices video is out, then you may watch that before doing your HCF LCM paper 2. Okay, rational and irrationals. Now we get to the I think you might remember what these are. Rational numbers are written, oh my god, rational numbers are which we can express in terms of a fraction in a form p over q, where q is not equal to 0 and p and q are in their simplest forms. Terms. Okay, now what does this mean? Example, we have 2 over 3. This is in their simplest form. Okay, simplest terms. Why? 2 and 3 cannot be reduced. 2 is not in a table 3 and 3 is not in a table 2. So this is the simplest form. Simplest form of fraction. If we have 6 over 9, however, this is not in its simplest form. We can still reduce this by dividing by the table of 3. We get 2 over 3. This is called simplifying fractions. Okay, I will go into the next video about fractions, decimals and percentages, about what these are and stuff in more detail. For now you need to know what a fraction at least is. P over q in its simplest forms, and q should never be 0. You know the saying, you cannot divide by 0. You get a explosion. Let's say that. Okay, let's say that. Math error in your calculator. Irrational numbers are the opposite. We cannot express them as a simple fraction because they are non-recurring and non-terminating. What do these mean? We will get to these in a second. Okay, these two are in here, but for now you need to know we cannot express them as p over q. Okay, example, take square root of 2, the famous example. It is like 1.414414 blah blah blah. You cannot express it as a fraction, no, because this is like repeating and does not no, it goes on forever and does not repeat. We do not know a pattern in the decimal expansion of square root of 2. That is why we call them irrationals. In the practice papers, okay, if we see a square root, okay, for the most bit, a square root which is not a perfect square, or a square root, a cube root, not a perfect cube. Okay, then you can say, hey, this is a irrational. Go. Um, yeah. If the square root has a fraction, and the fraction can be like perfect or perfect, and then this is also a irrational number, irrational quantity. Okay, so what does it mean to be irrational? You cannot express it as a simple fraction, and the most common ones you see is a radical not having a perfect number, perfect cube or square, or a fraction not simplifying to be a perfect cube or a square in the both numerator and denominator. Okay, and also remember, pi is also irrational. Okay, pi is also irrational. Keep in mind these two things. Okay, fractions represent parts of a whole number in the form p over q. P and q are integers and q cannot be 0. Yes, I repeated the definition, but come on, it's okay. You know what a fraction is now, at least. Example: 1, 2, 3, 4, 5, negative 5, 7, negative 49 over 36. This cannot be simplified. This is a perfect, okay, this thingy, 49 over 36. If we take the square root of this, we get 7 over 6. This is this gives a perfect number, and this is also a perfect square. Okay, these two, perfect square, we can take the square root and get a proper fraction. Okay, if these two are not perfect squares, example, 5 is not a perfect square and 9 is, this still gives us 5 over 9 square root. We cannot simplify this, sorry. Okay, so this, if we get like example 5 over 9, this is a irrational. Okay, because we cannot simplify this, cannot express it as a simple fraction in its lowest terms, so it's irrational. Reciprocals are the multiplicative inverse of a number. For an integer, example a, it is 1 over a. And for a fraction, it flips it. Example, d over b yields b over d. Okay, now this may look a bit weird, but I'm sure you guys won't mind why it looks like way. You know, this thingy. I want you to keep this in your head, please. I have put so many questions about reciprocals. Okay, that you cannot then forget what a reciprocal is. That's how important we need to know reciprocals. Everything is important, but sometimes people overshadow this. Decimals are numbers with digits past the whole point, meaning this is like 249, 245. This is the whole point. Okay, or people call it the decimal point, decimal dot, decimal something. Okay, these are digits past the numbers past the whole point with digits. Okay, numbers with digits past the whole point. Sorry. Terminating decimals. These are decimals which stop after a certain number of decimal places. They have finite digits and are after the decimal point. Example: a half has 0.5, 5/8 has 0.625. They are called, quote, terminating because they stop, i.e. terminate at some point. Okay, here we see irrationals are non-terminating. They go on forever. If a number is terminating, then it's irrational. If it's non-terminating, but it is a repeating, it is irrational also. Don't worry, I will make a table of what you need to know. Remember, if it's terminating, meaning it stops at a point, it is a rational number. If it is repeating, if you see that it's going on forever, but it has a set pattern. Example, in 1/7, it is 1, 4, 5, 2, 8, something like this. But this pattern repeats on and on and on, on and on and on. This is a non-terminating but repeating in a fraction, meaning a rational number. Recurring decimals. Okay. Yes. These are decimals which repeat the same group of digits infinitely. Example, 1/3 repeat the digit 3 like infinitely. 3, 3, 3, 3, 3, 3, 3. 1/7 repeats 0.14285, 14285. Like this block is repeating in 1/7. They are called recurring because the digits repeat, meaning reoccur or recurring. So you know what a recurring decimal is. So to devise what can be a rational, if it's terminating, repeating, or non-terminating, repeating. So if it's this group, non-repeating but terminating, meaning it repeats, it goes on forever, but it has a set pattern, it is a rational number. If it has a set pattern, but it if it's not repeating, if it does not have a set pattern, but it stops at after some digit, it is a rational. Okay, this first point here. If it is repeating but non-terminating, okay, if it goes on forever but it has a set pattern, then it is called a repeating non-terminating number. If it is repeating and terminating, example, 33/100. This, you can take this as an example. This is a rational number also. Example, this is 0.3333. What is this? This repeats, but it also ends after some decimal places. So this is a repeating and terminating. So what do we say? It is a rational number also. So these are the properties of rationality of a rational number. If it is non-repeating and non-terminating, it is what? Irrational. Okay, now recurring decimals are written with dots on the first and the last digit of repeating decimal. If there is few or more digits repeating, we use a bar over them. Okay, this is like copy paste from my original notes, So example, normally you would have 0. This dot means this digit is repeating. These 3 dots meaning this group of digits is repeating. Okay, and if there's a bar over it, meaning the group is repeating, this group is repeating. Okay, I think there's like, I've not seen a paper using this bar notation before. Okay, comment down below if you have, either from 0607, 1424, no, not 1424, or like 0580. Recurring into fractions. Now this question is answered in the practice file. I will give it to you guys. Okay, if you cannot do this, okay, then I do not blame you, but you need to be able to know this. If you want, I can make a separate video for this. Okay, recurring into fractions. To be able to convert between a fraction and a recurring decimal, we use multiplying 10 to the n, where n is the count of repeating digits. Let x be the repeating decimal. We subtract 10 to the n x by x and obtain an equation ax is equals to b, where we solve for x, simplify, and done. Example, we want to convert our recurring decimals into fractions. Okay, let me break it down what I just said, what revelation brought upon. And this is a very bad representation. I think I might just fix this. Oh, and I'm not giving you guys this file also. Yeah, so why am I bothering to fix this? I'm not giving you guys this file. Said who? And we can have this be green. There, I think this works much better. So, example, we have 0.17. We see that there is only one digit repeating, meaning we see that there is one digit repeating. Hence, we get 10. The first number that we have is 10x. If we have two digits repeating, we have 100x. If we have more, like the 3 digits repeating, it's 1000x, and so on. Okay. Next, what do we do? We subtract this by the original number. Okay. Now, be careful of the placement of the decimal dot. Okay, the decimal point. This is crucial when doing decimal computation. Okay, like subtraction and addition by decimals. You have to be mindful of where you put the decimal dot, or how you order the digits. If you like go lazy, 1.777777 as 0.17777771777, then you won't be like, it would be a bit confusing, like where is where. So you want to be as clear as possible. Example, this dot is directly above it. It's 1 and 0 are above themselves, and the 7 1 is above each other, and the 7 7 7 repeat. When subtracted, this becomes 0 0 0. These all are repeating, so you have like this repeating zeros. 7 minus 1 is 6, and 1 minus 0 is 0. Repeating the trailing zeros, we skip them. Okay, we skip writing them because it's like infinite. 0 is literally nothing, it's just a placeholder. So you just write nothing. 1.6, boom. So you can see in all the examples, we do the following thing. Now, if this number is a decimal, then it's okay. Just multiply it by 10 on both sides. Example, you multiply 10 on both sides, you get 90x is equals to 16. Here you get 990, x is equals to 121, etc. And here, if we get a normal number, then that is good also. Here I did not have like the alignment thingy for this, sorry. Okay, like for these other two examples, but if we write them properly, as I told you, 123.123, 3123, blah blah blah, 0.123, 123, blah blah blah, we can see it indeed gives us 123. These all cancel out, so we are left with 123.0. This we get 12.32323, blah blah blah, and this is we multiply by 100. So the original number was 0.123323, blah blah blah. You can see these all align up, and you get 2 point. Oh no, oh god, I'm very sorry. Okay, you guys can skip this. This gives us what? 99x is equals to 12.2. You get x is equals to 12.2 over 99, and this gives us a very ugly number, 495. Now don't be scared. This number that you get, you'll get an easy number. Okay, I just chose a very terrible example for this, but you will 100% get an easy decimal expansion in your paper, promise. Okay, you guys can see this. For example, here there is no mistake. It simplifies to 8 over 45 because 16 over 90 they have a 2 common. You get 8 over 45. If we have this, okay, 123,999, we just divide and you get this weird fraction thingy. If you guys cannot simplify, then you guys may need to do some practice of simplifying fractions. Okay. For recurring decimals. Percentages. This is the final thing before ending the video. Percentages are a way to tell a part or portion of some quantity. They are represented by x%, by a percent being 1 over 100. Percent means to divide by 100, or a multiplicative inverse of 100 is 1 over 100. The reciprocal of 100. Divide 100 times 1 over 100. Same thing. Okay, we'll revise this in fractions, percentages and decimals next video. To turn percentages into fractions, you basically divide the number by 100 or multiply by 1 over 100. See? Example, 20%, you get 20 over 1000, or 20 times 1 over 100, so you get 1 over 5. To turn percentages into decimals, you basically divide the number by 100, aka shift the decimal places to the left. This second thingy I wrote, you will see this in standard form. Okay, so for now you need to know it is divides the number by 100. Okay. There will be also some practice questions about conversions between fractions, percentages and decimals at the very end of the file. So yeah, you better check those out as well. I hope you guys understood today's lesson. If you want me to revise anything in today's video, then comment down below. If you want to like, subscribe and share for more videos like this. Okay, so that I can see that you guys do support me in covering the syllabus. So yeah, goodbye and see you in the next episode, where I will cover the next part of the syllabus. Bye.